All hear me?
Not quite.
There you go. Can you all hear me now? Okay, great. Is there a laser? Okay. So thanks to the organizing committee for setting up this wonderful meeting and for our chance to give a talk on our work on this very interesting problem today. So to get right started, I would like to visit the diagram that we've all seen thousands of times, perhaps, which is this mass, this radiation here with the Earth, the mass semi-major diagram here, which as the result of 5 years of concentrated work and discoveries have now starting to identify discrete populations that are appearing in this diagram. The hot Jupiters here at close in radii, the more giant planets here at about 1 astronomical unit, and now the growing populations, perhaps dominant, of the super-Earths down here. So these, any theory would have to explain why this diagram is breaking up perhaps into these discrete populations. How do we start with 1/100th of an Earth mass core, which would be down in here, and end up populating this part of the diagram? What kind of tracks would you connect between such regions and these objects up here? Okay, that's the issue. Now, the theoretical view that we've had that guide us to this issue, this one championed by Ida and Lin, Mortacini and others, that this is a statistical problem, that there's a variety of disks controlled by many different kinds of parameters. With those parameters and models for time evolution of such disks under viscous evolution, you can, in such a diagram, try to find what sequences match the diagrams, the data up in here. A very important result of this work is that migration, standard migration theory in a homogeneous disk fails, and it fails rather badly. And this sequence of models shows you need to slow down the migration of small mass cores by type 1 migration by factors of 10 or more. Okay? So this is a key problem in the whole issue. Otherwise, everything will be lost to the central star. So what we will be doing is first of all, addressing how you stop such rapid migration by planet traps, and then how you would build tracks in this diagram to connect low mass cores with the data. Okay? That's where we're going with this. So first of all, Yasuhiro took you through the argument for traps. I'm going to divide my talk into traps, tracks, and statistics. Okay? Traps. There are many ways that you, in a change in density contrast or a thermal change, that regions that we've all come to respect, such as dead zones, ice lines, heat transitions, which abound in disks, should be places where you have zero net torque. You can prove this mathematically, and Yasuhiro showed you at least one of the arguments for dead zones for that point. So this seems to be very clear, okay, that these exist in disks. Second question, traps are not static. In a time-evolving disk, they move inwards, but they don't move at a migration rate. That would be far too fast. They move at the scale of disk evolution. That's a viscous time. That's 10 to the 6 years, not 10 to the 5 years. That's how you solve the rapid migration problem. The trap is essential. What doesn't get stuck in a trap stays at low mass and quickly flies into the central region. Okay. You add this now, in the trap is where you undergo this core accretion, nicely reviewed by Roman just a few moments ago. And so by combining how a trap moves with how a planet core accretes in that moving track center, you can create the evolutionary tracks that I'm going to just show you. Okay? Beyond that, once you start knowing how to do this, you can then start doing statistics. I'm going to show you that actually in this theory, there are only two real basic parameters. It's how long a disk lives. Darn. Get back here. It's how long a disk lives and what the accretion rates or the masses of those disks are. Okay? So I'm going to show you those are the control parameters for these tracks. So first of all, where Yasuhiro left off, very important thing is that the motion of tracks, where it is in radius, here's the disk radius. So times equal to 0, you've got a trap here out at a few AU, beyond 10, and maybe tens of AU here. As time goes, you move this way, and at the time, the variable here is the accretion rate. Analytically, you can show these are power laws of the accretion rate. Okay? So you move this way with time as the accretion rate falls from 10 to the minus 6 to 10 to the minus 10. You move inwards slowly. Okay, where do we go from here? The accretion rate is changing with time, right? The disk is evolving viscously. So you do the standard kind of theoretical model, say self-similar solution, Linden, Bell, and Pringle, or more recently Chambers. I don't think the details will matter very much. But in those standard mathematical solutions, you know how the disk accretion rate evolves in time, is this power law. But there's a kicker. What finally, as we learned a few days ago, what finally kills a disk off sharply is photoevaporative flow. Nice talk by Alexander a few days ago. So there's a rapid truncation here due to photoaccretion. Now note, here come the two parameters I warned you about. One, scaling of the accretion rate. Very important for motion of the trap. Second, the disk lifetime, that is to photoevaporative losses, okay? These two will control your tracks. Okay, now let's add core accretion to this, phase 2, where you get the track. Nice review here. 3 phases in the evolution of it. Remember, we're evolving in the trap is about 10 to the 6 years. So the rapid oligarchic growth of the planetary core here is over 10 to the 4, 10 to the 5. That's very fast. Well, instantaneously on the disk evolution timescale, almost. Then we've got a few million years here, gradually drawing down the first part of an envelope. And then, as the last talk indicated, we have a critical mass, and we rapidly accrete here. Very short time. So this is fast. We quickly grow in mass, very slow evolution, and here very quickly get up to the kind of towards a critical mass. So let's put those ideas together now in a track. I'm going to take you through this. It's very straightforward. Okay. Let's take here the track of a dead zone. Here's a radius. We start a track here at 1/10 of an Earth mass here, an embryo. Okay. Here's the mass. Here is the semi-major axis. You start here, and the first pace is oligarchic growth, right? Very rapid accretion. You hardly move at all in 10 to the 6 years this way in the diagram. I think my laser is dead. To the left. But you, in 10 to the 4 years, you shoot upwards in mass until at phase 2, you hit the critical mass. Well, not quite the critical mass, short of it. Now in this coming back to the left in phase 2, you're accreting very slowly, that bit of an envelope. Okay? So the planet motion, the motion of the planet trap drags you to the left, to shorter orbital radii. Then you hit the critical mass at that point of phase 2, the end of phase 2. Now you rapidly increase in mass, over a few, much less than 10 to the 6 years. So you shoot upwards again. If you're massive enough, you now open a gap. When you open the gap, you quit feeding. You've stopped. Now you will be just dragged inwards to lower orbit by not the trap. You've fallen out of the trap here too. You go by type 2 migration this way. And then finally, photoevaporative effects zap the disk and you're done. There you are. Now do this calculation for each of the 3 traps. Okay? Put it all together and this is what you get. I seem to have hexed this electronics here somehow, so maybe I better go back to the laptop. So here are the tracks, and you can see now here's 3 different ice lines showing you the green. The red is the dead zone. You see that you very quickly climb up from a dead zone trap up into the giant branch of the masses there. You also have some ice line traps that get you very quickly up here. Which one? Middle? Very good. Thank you very much. So you notice that in this excluded region in the old Ida and Lin theory, where you shouldn't expect any planetary to form, you do have some tracks connecting here. These do not become giants. These are going to threaten to become hot Jupiters over here. Okay? Here we just simply lay down a bunch of different embryos here and watch how they travel up these tracks. Let's compare that with the data. Here's the data. Here's from Mayor. Very well, best determined RV data subsample published a few years ago. And you see how nicely these can connect up with this region. A lot of tracks piling up into here in the giant. and then over to this region. The super-Earths aren't shown here. I'll show you in a moment. But you can already see the vestiges of a pileup over here. Let me make that precise. So let's now go to the third part of the talk, statistics. All right? So let's divide up. Here's a more recent compilation, including the Kepler data. Let's divide up our mass semi-major axis diagram into 5 zones. The hot Jupiters over here. Let me just go through this quickly. There's the hot Jupiters over there. That's kind of an exclusion zone. Here's another planet, zone 3. A lot of guys in there. Observationally, that's clear. Here are the transits. Not too many in there. I mean, the imaged planets, very important. Hold on to zone 4 in your head. And zone 5, the super-Earths. All right. So, in order to now do the statistics, we want to look in our 2-parameter phase space here of disk lifetime and disk accretion rate, these 2 parameters. We're going to look at basically what fraction of the tracks end up in zone I, where I is 1 to 5 for each of these parameters, okay? Divide by a number of tracks that you start with. It's very simple. Simple to say, hard to calculate. And, but here, so now these are kind of probability diagrams. Here is the lifetime of the disk, between 10 to the 5 and 10 to the 7 years models. Here are the accretion rates, high here, low down here. To get hot Jupiters, you have to have a long-lived disk and at a fairly high accretion rate. You have a massive planet after all. What about the exclusion zone? Next. It shifts over here to slightly smaller timescales, those kind of disks, neatly avoiding this hot Jupiter zone, by the way. And up here again at reasonably high accretion rates. Zone 3. Large swath of models get you to zone 3. This is the most popular part of the giant diagram. And here a wide range of things. Again, lifetimes of disk here, a few million years in that category. Accretion rates tipping down to lower accretion rates. This by area in this 2-parameter phase space is the largest. Zone 4. Nothing. Isn't that interesting? A few weeks ago, we were worried about this, but these calculations are done for CTS's stars, by the way. However, in this meeting, we've learned how these surveys that have been going on for the last few years have come to completion, and it's clear that there aren't planets, giant planets, much beyond 10 AU, and we don't find them in these calculations either. And to zone 5, the super-Earths, here we're down, again, you should be living a long time here, but the accretion rates are low here, which makes sense. You're forming lower mass planets, but it's in this part of this phase space that you can connect up with the super-Turfs. And in this picture, the super-Earths are failed Jovian cores. They never get to the point where they draw down much gas. They just don't quite reach that point. So if we look then at, we can ask the questions, okay, we've got feeding these zones from different kinds of traps. How does that work out? What fraction of planets, say, we're in a dead zone, end up in, as a hot Jupiter, say? Okay? So here, for each zone, hot Jupiter, say the giants and the super-Earths, you can see the fraction, the contribution from each kind of trap. So dead zones contribute quite substantially to, this is the percentage of all the tracks that we run, most to the zone 3 region. Equally, the ice lines between these two, these populate the zone 3 the best. So if ice line was emphasized in work by Ida and Lin as an important place for barrier, but equally important in this calculations are the dead zones. The heat transition traps provide predominantly the super-Earths. You don't get much accretion in the super-Earth track as you move along in the data. So now let me just, I'm almost done here, a couple of slides. Here, if you integrate over all the tracks, over all the, and this is done not by Monte Carlo simulations, but by Gaussian probability functions laid on most likely values for each of those 2 parameters, and then computing here, this is the mass going on down this axis between 0.4 and 1.6. This is the percentage of planets that end up then as a function of mass in these zones. So zone 3 you see is quite low, below 0.7 solar masses. You don't have many giants. But at 0.7 solar masses is the first time that you have more giant planets than you do with super Earths, with the low mass planets, which tend to be falling down in frequency here. So this also seems to match up nicely with the data. This transition. It's not a hard transition, but it's a transition nonetheless. Here's my summary. Tracks plus core accretion allow you, this fact that a planet is trapped actually means it's very important. It's an unavoidable part of this whole business. If there's anything about this talk, I hope you remember, it's that where a planet feeds is important, not just how it feeds. Okay, so this gives you these nice evolutionary tracks. We find that dead zones and ice lines feed the giants here. And heat transitions in dead zones feed the hot Jupiters and the low mass planets. We have a very definite pileup at 1AU. I could talk at length about that. One of the reasons you have a pileup there is you rapidly grow up in mass, you open a gap, and then you move slowly inwards by type 2 migration. And that slowness, and the disk goes away, and you're stuck at 1AU. You know, the train has left the station. Super Earths are failed cores, and I will just leave it at that we don't have many tracks, at least for CTS systems, to large radii. And thank you very much.
Okay, so, yes, you want to grab a mic?
Hi, it's Bruce McIntosh. I just wanted to comment on the absence of planets in the large radii. One thing to keep in mind is that the statistical power of direct imaging searches is actually quite weak compared to the power of Doppler surveys. And so it would be perfectly possible for there to be as many planets from 10 to 50 AU as there are from, say, half an AU to 2 AU, and be consistent with the low discovery rates that have been found so far.
Okay.
So not to say that I know there's lots of planets there, but it's an overstatement to say that we don't know that we know that there's an absence of planets that's statistically strong compared to the ratios of
So
Doppler
interpret my
planets.
remarks as theoretical excitement over something.
Yeah. So,
I should be more cautious about
right.
that.
Wait till the next round of surveys are completed. Okay. I think the survey power beyond 50 AU is pretty good, but in the 10 to 50 range, it's equivalent in power to a Doppler survey of 50 stars or so, which would get you about a planet in a decade of mass semi-major axis space.
Yeah, thank you.
That's
That'd be a good point.
fine.
Okay. Over here, Ralph. Really exciting stuff. Are your results consistent with the radial velocity findings that, you know, you're getting 1 in 100 stars with a hot Jupiter, 1 in 10 with Jupiters,
We haven't looked into
most stars with the little guys?
Yeah, we haven't looked into that detailed statistic yet, but I agree that's an additional interesting constraint here. Also, I should say in these models, in Yasuhiro's thesis work, he did compute some models for A stars, but we haven't. There you do have a few tracks that connect up. And maybe that's part of the explanation here, but there are just a few there.
Do you have questions on it? Yeah. Yeah.
Great minds.
Yeah. It looked like you were producing too many planets in your Zone 2 exclusion zone. Did you want to comment on that?
I don't remember. So I would have to sort of. But could you explain why you think it's too many? You have a number there that should be.
Well, it just looked like comparing the numbers that you were getting in Zone 2 and Zone 3. You were saying Zone 3 we have lots. Zone 2,
Right.
not
Yeah.
as many, but it's still, you were getting quite a few.
So,
And it
yes.
just seemed like the ratio between the two of
So
them
whether
was
we
too
could
high.
get a factor of 3 there or not.
Yeah.
I'm not sure if we've actually computed that for these models yet. The probability density contours. The last diagram may actually say something about that. Let me go back here. So I think you're referring to this here, zone 3 versus zone 2. So there's the prediction here. So it's a factor that's significant. Okay? I'm not, again, we don't have a data point here from the observations, but it is a significant difference.
One last question here.
So how does a planet multiplicity fit into this model, in the sense that we find it looked like that there were possible situations there where you would have less massive planets somehow having to be inside more massive planets, despite the fact that they'd form outside the more massive ones? And
Yeah, no, I completely agree. It's an interesting question, and one that we want to be pursuing next. If you saw originally on the Yasser tracks Yasuhiro showed for the evolution of the planet traps, there are points where you can bring planets quite closely together. And so there'll be some complex dynamics there that'll matter. That's where the point where multi-planet interactions will matter. Otherwise, the tracks are fairly wide separated, and we can get away, I think, with this kind of a single planet modeling. But these points may be very interesting indeed.
Okay, thank you very much, Rolf.